are from Group 5 and we are doing Experiment 6, which is Sedimentation Studies Apparatus. I'm Afika.
And I'm Abdul Majid.
I'm Amirul.
Hello, I'm Lynn.
And I'm Aida.
What if we run away? What if we
The first one is introduction. So, sedimentation is the tendency for particles in the suspension to settle out of the fluid in which they are entrained and come to rest against a barrier. This is due to their motion through the fluid in response to the forces that acting on them, which are three. The first one is gravity, second one is centrifugal acceleration, and the third one is electromagnetism. Sedimentation Study Apparatus is a benchtop unit designed to allow students to study the different characteristics of sedimentation. Students shall be able to determine not only the effects of initial concentration and initial suspension height on the sedimentation rates, but also the effect of the particle size distribution that using of flocculating agents. Students shall also be able to construct the settling rates curve from a single batch experiment. At the beginning of a batch sedimentation process, the solid is uniformly distributed in the liquid. After a short while, the solids have settled to give a zone clear liquid. In a sedimentation experiment, the applied force accelerates the particles to a terminal velocity at which the applied force is exactly cancelled by an opposing drag force. For small enough particles, the drag force varies linearly with the terminal velocity. Similarly, the applied force generally varies linearly with some coupling constant that depends only on the properties of the particles. Hence, it is generally possible to define a sedimentation coefficient that depends only on the properties of the particle and the surrounding of the fluid. So, what are the objectives of the experiment? First one is to study the effect different initial heights and concentration on the settling rate, and the second one to study the effect different of flocculants on the settling rate.
What if we're hard to find? What if?
In this experiment, we are focusing on the sedimentation that caused by the gravitational force. Gravity sedimentation is a widely practiced operation in many industries. Process-scale sedimentation equipment is generally designed after performing tests on a small laboratory scale. The laboratory tests identify the appropriate settling regime and can also generate operating data suitable for the use in the design. Laboratory tests may also be employed when investigating the performances of existing process-scale sedimentations, identifying possible operating conditions and settling behavior. At the beginning of the experiment, the solid is uniformly distributed in the liquid. After a short while, the solids have settled to give a clear liquid zone. The process will continue, and finally, when the weight of the solid is balanced by the compressive strength of the aggregates, the settling process will stop. The process can be made faster by adding flocculants. Flocculant is a substance which promotes the clumping of particles, especially when used treating wastewater. There are many examples of flocculant, and aluminum oxide is chosen in this experiment. The flocculants can come in variety of molecular weights, charge densities, charge, and of course in many kinds of forms. It can be divided into two categories, which are anionic flocculants and anionic flocculants. The anionic flocculants basically are usually based from copolymers of acrylamide and acrylic acid. These anionic flocculants have negative ionic charge, and it works by binding with residual cationic charges on flocculants absorbed to coagulate solids. The effects of flocculants towards the sedimentation rate will be shown in the results and discussion parts.
Lights start flashing like
So in this experiment, each unit consists of 5 cylinders, beakers for solution preparation, and stopwatch to record the settling time. Next, the operating procedure includes 3 steps. Firstly, filling the cylinder. This is when we are preparing the solution in the plastic beaker and then transferring it into the cylinder. Next, we empty the cylinder, and last but not least, back to panel illumination. This is when we plug the power cord into the power socket. And now for the procedure, experiment A. Before we start our experiment, we made sure all the cylinders are empty. If the cylinders on the panel, carefully pull the cylinder from the panel. Before we transfer the solution into the cylinder, we prepared all the solution in the beaker. Then we poured all the solution into the cylinder, like the pictures beside on my left. The solutions in the cylinder is stirred. We record the initial time, and then the final time and the height of the clear liquid interface. Z every 5 minutes interval were recorded. Before we start our experiment, we made sure all the cylinders are empty. If the cylinder on the panel, carefully pull the cylinder from out of the panel. In this experiment, we prepared the flocculant by mixing 20 grams of aluminium oxide in 1 liter of water. Before we poured into the cylinder, we prepared 5 different sets of cornstarch in the beaker first. Then poured all the solutions into the cylinder, like in the picture given on my left. The power cord is plugged into the power socket to turn on the back panel illumination. The solution in each cylinder is stirred. The initial time and the height of the clear liquid interface is taken at every 5 minutes interval. The final time and the final height for each cylinder were recorded. All the results were tabulated in table 2A.
My youth is yours, tripping on skies, sipping water.
For the safety precaution, always observe all the precaution in the laboratory. Always wear protective clothing, shoes, helmet, and goggles throughout the laboratory session. Always run the experiment after fully understanding the equipment and procedures. Inspect all the cables for any damage to avoid electrical shock. Replace if necessary. Inspect the unit, including tubings and fittings, periodically for leakage and worn out. Leakage might cause damage to equipment by corrosive chemical in the long run.
Throughout this experiment, there are several types of error that need to be taken care of. The first one is parallax error, where the eyes are not perpendicular to the scale or the height when we measure the clear interface. So to avoid this error, we must make sure that the eyes are perpendicular to the height. And the next one is the human error, where the height recorded is not simultaneously taken within each time interval, which is 5 minutes in our case. So to improve this, the height recorded should be taken using a digital device sensor so that it can be more accurate. Besides, there is also zero error that can be indicated the weighting balance that used to weigh the cornstarch and flocculants. Before using the scale, we must make sure that the scale or the weighting balance is being calibrated back to zero for each sample. Other than that, the cornstarch solution are also easily accumulated at the bottom of the beaker within a short period of time. To avoid this, make sure to stir the solution before pouring them into the cylinder. Last but not least, the error that occur comes from the apparatus itself, which is the panel lighting value. The intensity of the light provided in the apparatus is very low, which can cause the difficulty while taking the reading as the interface cannot be clearly seen. Thus, the apparatus has to be constantly monitored to sustain in good condition.
Cause we've no time for getting old. What about timeless souls?
Okay, next we go to discussion. For experiment A, the manipulated variables are different concentrations of the cornstarch suspensions and the initial heights of the suspension in the settling cylinder. To achieve this, 2 different masses, 50 gram and 100 gram of cornstarch powder is mixed with 2 liters of water in 5 different beakers and filled in the settling cylinder based on their respective heights. At every 5-minute interval, the height of the clear liquid zone is recorded. As clearly seen in the results, where the higher concentration has a slower settling rate. This means the cornstarch particle in the higher concentration suspension take a longer time to travel to the bottom of the cylinder due to hindrance from the other nearby cornstarch particles. This is known as hindered settling. So, therefore, when we compare cylinder 3 and 4, cylinder 3 settles faster. When comparing 1 and 2, cylinder 1 settles faster. Next, we go to the part B of the experiment. For part B, different volumes of flocculants, which is aluminium oxide, are added to the original mixtures to study the effect on their settling rates. So the settling rate is higher in lower concentration mixtures, as when comparing cylinder 3 and 4, cylinder 3 settles faster. When comparing 1 and 2, cylinder 1 settles faster. Therefore, when we compare to the settling rate values of part A, the results are rather similar, but in certain cases, it is seen that the settling rate is higher under the use of flocculants. This is because when using the flocculants, the cornstarch particles become further coagulated, which causes them to settle to the bottom of the cylinder faster. So therefore, these are all the results.
My youth is yours.
And the last part is conclusion. After the results and discussion that we have shown, it can be concluded that the settling rate is getting higher as the concentration suspension gets lower. This can be proved by the results that we are getting, which in the same amount of the cornstarch powder, the one with the lower height of the solution will settle down faster. The usage of the flocculants has given an impact on the settling rate. The function of flocculants, which is to accumulate the solid particles, has made the settling process to be faster and thus giving a high settling rate.
My youth is yours.
This is an illustration of free settling, where the bigger particles settle faster than the smaller ones. The red's the biggest, the blue's intermediate, and the yellow's the smallest. And basically they're settling without any interference with each other, which is why we say free settling. Happens at low concentrations. If we move up above a concentration of about 1% by weight, then we move into hindered settling, and you can see now we have the red, the yellow and the blue particles again, but they're not settling like they were with free settling. They're settling what's called en masse. They're settling under what's called hindered settling, and if we were to trace the interface, that's the boundary between the settling solids and the completely clear liquid called the supernatant that's left behind, then that interface plotted against time looks like the graph on the right. It's a straight line and then reaches a period where it starts to curve over a little bit and eventually becomes flat when everything's settled out. So that's hindered settling, and that's the classic height against time plot, and it's the plot of the interface during hindered settling. We can get a lot of information from that plot by careful analysis. And this is the illustration of the zones that occur. There's the interface plot on the left hand side now, and if we take a fixed point in time, the zones are shown on the right. There's the supernatant, the clear liquid, the original concentration zone, variable concentration zone, and then sediment at the bottom, and that's at a position, fixed position in time, t. And here is some sedimentation. This is a fairly fast sedimentation. It's normally a much slower process than this, and typically performed in batch jars like this, measuring cylinders like this. The good news from the design point of view is that the sedimentation rate is not dependent on the vessel area. So laboratory tests using measuring cylinders are very good for designing industrial thickeners much bigger. That's industrial devices much bigger in area for separations. And you can see there was an interface, and if we zoom in a little bit we can probably see that interface a little bit better. There's no, here we go, there's another shaking up and settling, and you can see the interface quite clearly now. The supernatant liquid is not completely clear, but it's not bad. There's just a very few solids left there. And if we were to plot this against time, we would see that it had a straight line and eventually a curve, and then when it was fully settled it would just become a plateau. And this is an unusually fast sedimenting system. Most things settle much slower than this. Sedimentation is very much light because it's cheap, it's gravity driven, so the energy requirements are very minimal, and you can see that the interface is now just coming below the gradations on the measuring cylinder, and it's pretty much going to finish somewhere around there. So that was a very high concentration. If we had that much lower concentration, it would have settled much faster. Here we have a more realistic system. This is gypsum, which is flue gas desulfurization gypsum from power stations. 5 measuring cylinders at different concentrations. In fact, the lowest concentrations on the left, the highest concentrations on the right. And we're not going to wait for those to settle. Here they have settled, and you can see that this isn't fully settled. This is at the same period in time, and on the left we've got quite a low sediment, and on the right we've got quite a high sediment. They're still settling, and if we zoom in a little bit, you'll certainly be able to see the clarity of the supernatant. Again, it's not crystal clear, but it's not bad at the higher concentrations. That's the highest concentration on the right, and then those 3 there are reasonable concentrations, and the 2 lowest concentrations on the left, you can see clearly that again the supernatant is not bad, but it's a little bit cloudy.